Good afternoon, everybody. Welcome to our session, afternoon session on what we call a QPAC, which is a quantum and I don't remember exactly. So this is quantum computer and information processing. We have the chance to have two talks, one tutorial from Craig Kidney that I will introduce, and one contributed talk from Elie Gouzien. So let me introduce you Craig Kidney. Craig, we have the chance to have a talk from Craig. Craig, as we discussed just a minute ago, doesn't have any degree in physics. He's a computer scientist that he mastered in computer science. And then he was hired by as a software engineer in Google and got into like quantum mechanics. And you just told me that basically before getting into quantum mechanics in Google, you basically didn't really appreciate what was going on in quantum physics. And then he started to develop some software, some tools that were specific to quantum physics, and get involved in this important project in Google to build a quantum computer. And now he's working actively, and he's making and this is the reason why we invited him. He's making like some estimation of the resource, and this is one of his job. I think he will explain you more about this, but to estimate the resource needed to run a quantum computer, a universal quantum computer. So please, Craig, we are looking forward to your talk.
All right, I guess I'll get going. You can't see this little video tab on the right-hand side, right? That's only on my screen. Like you can see the entire slides, I'm not including them?
Yeah. This is
okay, good. All right, so looking back at the abstract that I wrote for this talk, I sort of realized as I was making the slides that it was far too ambitious, and so it has been cut down a little bit. In particular, most of the surface code stuff is not going to be mentioned because I don't have time to cover how computations are embedded in the surface code, and also how you go about taking things that take a lot of time and turning them into things that take a lot of space. And instead of mostly going to be talking about that second thing. And I think that's a little bit appropriate because I think the talk after mine is actually about how you take something that uses a lot of space and make it instead use a lot of time. So maybe we'll have a little bit of a theme between the two of them. So an outline of what we're going to cover. I'm going to review a technique known as gate teleportation, where you combine teleporting a qubit from one place to another with applying a gate to that qubit using some resource state that you've prepared ahead of time. And in particular, we're going to be focusing on a simple case of this, where the corrections that you have to do to complete the teleportation are so simple that you can basically track them outside the quantum computer without ever doing anything different to the qubits. Then we're going to get into operations where that's not the case, where we're sort of touching a little bit more on the surface code stuff in terms of the operations are not native to those codes and they require more complicated corrections and require preparing special states called magic states. And once we've covered that, we'll get into really turning this into a whole way of performing quantum computation, where instead of being limited by your code distance, like how many times you have to repeat a particular set of parity measurements in order to complete an operation, you're instead limited by how fast can your control system figure out what the current set of measurements was and what the next set of measurements is. Then we'll try to apply that to an example, an addition, and then I'll give some caveats and talk about how this all does come together and actually affect the design of systems and the resource estimates that you make in the end. So let's get into talking about gate teleportation. So at a high level, what gate teleportation kind of looks like, and I don't really want you to take this description too seriously, but it's sort of like you have a qubit that's traveling forward in time. So I'm hoping that most people are familiar with circuit diagrams, by the way. It was mentioned to me before the talk that most of the people here are physicists. So I don't know how many people actually have seen this notation before. I'll just mention circuit diagrams. Time moves from left to right, and the boxes on the lines indicate operations to apply to the qubits. Gate teleportation, in this kind of simplified conceptual way of thinking about it, is sort of like you can take your qubit traveling forward in time and send it back and do a gate earlier on it before you come back to the present. Of course, there is a forward in time description of what is going on, where you create an entangled state and you apply the operation to that entangled state, and then you measure whether or not that entangled state is the same or different in both the X and Z basis from the qubit that you operated on. And this, if it was the same, then you're kind of done. The teleportation succeeded unconditionally. But if it's different, then based on these measurement results, you're going to have to apply different corrections down here. So this is sort of a fine little conceptual idea of what's going on, but what does this actually turn into when we want to run this on a quantum computer, when we actually want to do it? And essentially anytime you have a cup, like either a wire going from forwards to backwards or backwards to forward, that becomes a Bell basis initialization or a Bell basis measurement. So you to create this resource state that we're going to teleport through, you prepare a Bell pair. So literally the state 0, 0 plus 1, 1, which you can do by starting in 0, 0, applying a Hadamard to one of the qubits and then a controlled lock between them. And then you apply the operation that you eventually want to teleport to one side of that Bell pair. And then when you want to perform the teleportation, you perform the inverse of the Bell basis initialization. So instead of initialize Hadamard C naught, you go in reverse, you say C naught, Hadamard, and then measurement. And then based on the measurement results, you have to apply different corrections. So for example, if this measurement is 1 instead of 0, basically what that is telling us is that this qubit here that we operated on was bit flipped compared to this qubit that was coming in. And that means that technically, instead of applying U, we applied a bit flip, an X gate, and then U. And we need to get rid of that bit flip. And the simplest way that you could imagine doing that is you would undo U, you would undo the bit flip, and then you would redo U. So that's what's showing here as the correction. We undo U, we apply U dagger, then we apply the bit flip to undo the bit flip that was there according to the measurement, and then we redo U. This looks more complicated than having to apply U because there's more characters here, but actually these operations tend to be simpler. So for example, if U was a Hadamard gate and we had a bit flip, then conjugating a bit flip by a Hadamard gate like this gives you a phase flip, so a Z gate. And a phase flip or a Z gate is generally cheaper to apply than a Hadamard gate. So we'd be sort of happy to have to apply a phase flip correction instead of having to apply the Hadamard. There's actually a whole class of gates that have this property that their corrections are simple, that their corrections are phase flips or bit flips on various qubits. And these gate set is known as the Clifford set of gates. They're actually defined this way, that if you conjugate a product of Pauli's, a product of bit flips and phase flips by the Clifford gate, you get a product of bit flips and phase flips, which for us is an interesting property because it guarantees our teleportations have this simple property that they're bit flips and phase flips. Clifford gates also have other useful properties. So for example, if you only have the H gate, the S gate, and the C naught gate, that is a universal gate set for Clifford gates. You can take any Clifford operation that has this property can be decomposed into a sequence of Hadamard, S, and C naught if you want to. So we have a couple examples down here of conjugating a Pauli operation by a Clifford operation producing another Pauli operation. So if you conjugate the Y operation by S gates, you get the bit flip, or if you conjugate the bit flip on the control of, if you conjugate a bit flip by C naughts and you're on the control, the bit flip will propagate to the other side. Now, if we imagine that our whole circuit is Clifford operations or almost entirely Clifford operations, the fact that conjugating Paulis by the operations in the circuit produces other Paulis can be thought of in another way, which is that they propagate through the circuit in a nice way. So for example, if I tell you that you need to apply a phase flip at this point in the circuit based on some criteria that you don't know, you don't have to necessarily apply the phase flip right away. You could execute this Hadamard gate and then apply a bit flip instead. And these two actions on the circuit are completely equivalent. There's no way to observe a distinction between them. And as long as you're propagating through Clifford operations, you'll always have this property that you can just delay applying these Pauli corrections all the way to the end of the circuit. But essentially, you can just keep delaying them until every single one of the corrections has reached measurements at the end of the circuit. And at that point, the Pauli operations will either flip or not flip each of the measurements. So here I have an example where you have a bit flip earlier in a circuit, and it propagates through the circuit. And it so happens that this bit flip will become a phase flip on this measurement, so a Z gate, and a Y gate on this measurement. And what that means is this measurement result is going to be correct. So if we did not apply this bit flip operation like it's being shown here, this measurement operation would not have been affected by that choice. But this measurement, because a Y gate propagated into it instead of a Z gate, would be flipped. And what I'm trying to get at here is, if you have some error or some correction that happens in a Clifford circuit, you don't have to do anything different to the qubits in order to account for it. Instead, you can just keep track of how it propagates through the circuit and ultimately how it flips or doesn't flip certain measurements. And that is a perfectly valid way to execute the circuit. In fact, this means that after you've executed the circuit, I could come and tell you, oh, by the way, in the circuit you've already finished and already have the measurement results for, you needed to have applied a bit flip back here. And that's completely fine. You can figure out which measurements have to be inverted in order to account for that, as long as everything's Clifford anyway. And this is really useful if you want to do a lot of gate teleportation, because the corrections from gate teleportations through Clifford operations are always Pauli operations. And what this means is we can make a circuit that has a lot of gate teleporting, a lot of Clifford operations, and run it unconditionally, assuming that there are no corrections, and then go in after the fact and figure out what the corrections should have been, and figure out how they would have propagated through the circuit to affect the measurement results that we recorded, and get the final result. So this basically means that while we're running the circuit, there's no requirement that we're actively decoding the measurements and figuring out what they mean. We can do that all later. And this is a very useful property if you want to run an experiment and your hardware just doesn't support the kind of fast feedback that you need in order to do these corrections on the fly. So now here we have a quite complicated looking circuit on the right-hand side, which is kind of supposed to demonstrate this idea. So on the left, we have some circuit that we want to execute, which is a series of Clifford operations, C1, C2, and C3. And these operations are sequenced through time. So one happens, then the other, then the other. On the right-hand side, we also have C1, C2, and C3, but they're sequenced through space. So they all execute simultaneously on the quantum hardware. And then we use these Bell basis measurements and these Bell basis initializations to kind of weave the qubit backwards and forwards through these operations. So we have this top qubit, for example, which goes through C1, then it hits this Bell basis measurement, which sort of bounces it back, and we hit this Bell basis initialization, which again bounces it back, and we can go through C2. And that process repeats, and then we go through C3. And while we're doing this, we're generating all of these measurement results, which tell us how we have to bit flip or phase flip the output based on, well, the measurements we're seeing from the gate teleportations. Also, if we're not applying these live at the time, then we need to consider the fact that our input may also be have some bit flips and phase flips that we don't necessarily know. And those will also propagate through the system and affect the output polyframe. So at a conceptual level, by sort of ignoring the corrections, but knowing that they will be dealt with, we're able to sequence through space instead of through time. You know, there's a lot of details behind the scenes to make this actually work, but you can pretend that you just kind of have freedom to lay out your computation through space and time when you're thinking in this way. And that brings us to what if your operations aren't Clifford operations? What if their corrections aren't simple? And this gets back into error correcting codes a little bit. Like this part does kind of stand out in the talk as a little bit strange if we're only talking in terms of circuits and never talking in terms of error correction. But one of the problems that you run into error correction is a lot of codes only support some finite, well, every code only supports some finite set of gates. And in many codes, that set of gates is a Clifford set. And the natural question then is, how do you do general computation with just Clifford gates? And the answer is you can't. It's actually the case that the Clifford set is so well behaved that you can simulate it classically efficiently. People have known this since the 90s. But it is possible to kind of fix this non-Cliffordness and import the non-Cliffordness into the Clifford set by entering special states. And these special states do affect how we're going to incorporate this whole story into our gate teleporting story. So one way that you could imagine fixing this problem that you can't do a non-Clifford gate in a particular code is, well, some error correcting codes do support non-Clifford gates. So here I'm using the specific example of the T gate, which is a 45-degree rotation around the z-axis. What you could do is you could have a code which supports the T gate. You could take your qubit you want to apply to, and you could convert it into that code from your current one. Apply the T gate there, and then you could convert it back. It turns out that this ends up being quite expensive. I mean, really, everything you do to apply non-Clifford operation in the Clifford code tends to be expensive, but this ends up being particularly expensive. Like, for example, it would mean that you need maybe special hardware in one particular place on your chip that supported this other code, because different codes have different topological requirements for their connectivity. What we can do instead of this is something called, this is also called gate teleportation, although in this particular example, the qubit isn't moving from place to place. But it still has the same flavor in the sense that there is some particular state that was prepared ahead of time, which we call a T state. In this case, the T state is a uniform superposition of 0 and 1, where the 1 state has been phased by 45 degrees. So instead of a bell pair, which we acted on with the T gate, we have a plus state, which we acted on with the T gate as our special state. And then we perform this little circuit right here, and it turns out that the circuit is exactly equivalent to having applied a T gate. So instead of needing to figure out how do we apply a T gate in this code that doesn't support the T gate, what we can instead figure out is how do we get T states into this code that doesn't support T gates. And part of the reason that this can be so much more effective is if you make a mistake when you're entering a T state into your code, you can just throw that state away and try again. Whereas if you made a mistake applying a T gate to some qubit that you care about, you may destroy that qubit and you have to start your entire computation over. Ultimately, what this means is that when you're thinking in these terms of preparing magic states, you can use error detecting codes instead of error correcting codes. And error detecting codes tend to be much more efficient because they're allowed to throw results away when they look suspicious. So basically, the way this process works of getting these T states in practice is in every error correcting code, there's going to be some way to prepare a noisy version of a state. And also there'll be a way to apply a noisy version of the gate. We don't want to apply the noisy version of the gate because we might hurt a qubit that we care about. So we're much happier to prepare noisy states. And then what you can do is you can run destructive cross-checks on these states, which when I say they're destructive, I don't mean they're 100% destructive. I just mean they're mostly destructive. So for example, you might input 15 T states, run some destructive checks, which will destroy 14 of the T states and leave behind one of them. But the one that's left behind has passed all of these tests that give you much more confidence that it's correct. Now on this next slide, I have an example of a circuit which does T state distillation. You don't need to understand the circuit, which is good because it would take quite a while to explain all of the stuff that's happening here. The main thing that you need to understand about this circuit is it has the following important properties. First of all, if you run the circuit without any noise in the system at all, it will output a T state, which is what this little display is showing on the right-hand side. And secondly, if you insert a small number of errors in the circuit, in particular, if you insert errors in this line right here next to the T gates, it will detect those errors as long as there are at most 2 of them. Now, or it could be the case that every single qubit has a small amount of angle error, but those small angle errors will get digitized into small probability errors. And what it ultimately comes down to is in the computer world, we often describe the fidelity of something or how the uptime of something in terms of the number of nines. So here we have 3 nines of fidelity as an example coming into this circuit. So what that means is that these T gates 99.9% of the time do the right thing and 0.1% of the time do the wrong thing. And if that's the case, then when you have an output that survives the cross checks in this circuit, then the number of nines of fidelity essentially triples. So here we're going from 3 nines of fidelity to between 8 and 9 nines of fidelity. So hopefully that gives you at least some sense of where these states could possibly come from and why we would think about them in the first place. And now we're going to get into really more the details of how we use them in an effective way. So here I have another T teleportation circuit. So you might recognize this pattern of C-naughts and Hadamards bouncing a qubit back and forth, at least conceptually. And we're applying the T gate to one side of the bell pair. And then we notice that the corrections that we have to apply, instead of only being bit flips and phase flips, also include a Clifford operation. And we are not particularly happy about the fact that there is a Clifford operation applied here, because when we actually run things on the quantum computer, this means we have to do something different. It's not possible for us to entirely track this in the classical control system, unfortunately. But what we can do is we can make sure that the thing that is conditional is at least more convenient for us. So the S-gate is not ideal, at least in the context of the surface code. The S-gate is not ideal because it's not a transversal gate. It's not a gate where we just, apply some single shot thing to all the physical qubits and we're done. Instead, the S-gate is done in a complicated way, which I won't go into, but if our code distance was 30, for example, we would need to perform 60 rounds of measurements and like slowly deforming the stabilizer we're measuring to apply this S-gate, and it's just a whole thing. And ultimately what that means is when you find out the result of the decision of whether or not you're supposed to apply this S-gate, instead of essentially being able to do it almost immediately, there is this huge delay as you do these 60 rounds of things. We would much prefer for the conditional gate to be transversal in the surface code, to have this property that it only takes a single layer of operations. So for example, the Hadamard sort of has that property in the surface code, and measurement has that property in the surface code. So these two circuits are equal, but now in this circuit, the thing that is conditional is transversal operations. So there's a certain sense in which the delay in this bottom circuit is much lower than the delay in this top circuit, because until this operation is done, we can't do more things on this target qubit. The other thing that's useful about this particular circuit is that actually the thing that's being delayed on the target qubit is again a Pauli operation. And if we remember from before, Pauli operations have this great property that you can kind of apply them after the fact in your control system. So you can backdate a phase correction so that it actually happened here. And anything that you did in between, you just propagate through in the classical system. And what this means is that there's kind of this interesting period of time between when we've interacted the target qubit and this ancillary state, and when we know whether or not we want to apply this S-gate, where we can actually keep doing work on the target qubit. So this I think is a useful enough concept that I actually give it a name, which is a delayed choice gate. It's as if we get to do some stuff to the target qubit, which basically says, I might want an S-gate here in the future. And then we don't actually know right away whether or not to do it. Instead, our control is off in future land. And eventually, when we know the result, we rewrite history, we backdate all of our Pauli frame corrections in such a way that it's as if we did the S-gate or we didn't. And here on the right-hand side, there's a little bit more of a detailed view of what that looks like. So we have our qubit that we want to apply this correction to. We interact it with this special state that we prepared. And then during this waiting period, we can continue to apply operations to the qubit. And eventually, when we know whether or not we want to keep the S gate or not, we either do this Hadamard gate or don't appropriately. We do this measurement that tells us the correction that we want to apply. And then we backdate that correction in the control system and propagate it forward through the intermediate work that we did. So it's maybe clear why it would be so useful to just be able to say, I don't know whether I need to do a gate here right now, but it sure would be great if I could pretend that I did and just forget about the details, and or at least shuttle them off into some side part of the computation that isn't touching the stuff that I care about and need to continue operating on. But yes, it is useful to be able to do this. And I'll note, there are a lot of similarities between this concept and the delayed choice experiment. And I personally really enjoy this idea of, there's this thing out there in the world which people are quite confused about, or at the very least, in pop science articles, they're very confused about, and they make a very big deal about these delayed choice things. And we're here in quantum computing taking these paradoxes and turning them into tools to optimize circuits. Like it's almost, when you get used to thinking about these things, it's almost quaint to read a pop science article about delayed choice, because you just spent the day using that tool to make your circuit smaller. Anyways, once you have this concept of a delayed choice gate, you can combine it with the concept of a magic state, and you can actually embed this delayed choice gate with your magic state. You can pair them together. So instead of just giving a circuit a T state, which is what this part is here, we can also give a circuit this other part of the state, which can be used to correct the S gate that comes out of the T state. So that when you want to apply a T gate to a circuit, we again have this property where we have one interaction between the qubit we want to act on and the ancillary system. And then as soon as that interaction is done, we can begin doing other things with that qubit. And while we're doing those other things, the control system is working through the problem of, well, what was the gate teleportation? What are the corrections? How do I figure out whether or not to do this Hadamard? And then once I know that Hadamard, what's the measurement result? What are the phase corrections? And how do I backdate them? But it's very convenient to be able to work in this way, because as soon as we finish this, we can begin doing other things. You can actually take any gate and you can produce an automatic magic state for it. So again, here's a big complicated circuit that I don't expect people to understand the details of, or to be able to remember, for example. So this is, how do you apply a controlled control phase flip gate using this approach of automatic magic states? So like I said, you don't need to know the details here. The main thing to understand is it has the same pattern, which shows up every time. You have some initial state that you can prepare. And if you fail at making this state, it's okay to throw it away and try again. But eventually you get one. And then there's some period where you interact the qubits you want to act upon with that state, typically in the form of controlled knot operations or a parity measurement. And then once that is done, the qubit that you've acted on you can start doing other things too, while the control system starts working through this problem of, what are the measurements? What do I have to apply Hadamards to? What are those measurements? How do those affect the phase corrections? And how do I backdate them? But it's very useful to have this, because it lets you separate the problem of how do I quickly operate on my qubits from how do I deal with all of these gate corrections. And as maybe I've been repeating a couple times, what ultimately this comes down to in terms of what slows down the computation is this cycle of the control system figuring out what is the Pauli frame going into this interaction with the magic state, so that I can figure out whether or not this Hadamard occurs, whether or not this measurement is flipped or not, and that will allow me to determine the Pauli frame after this interaction. And then there'll be some other gate which looks a lot like this one. And once we know the frame there, we can figure out the Hadamard measurement for that gate and repeat this cycle. And this cycle ends up being the characteristic clock cycle of our quantum computer. So here I've tried to lay it out over space instead of just having a loop, and in order to give you a sense of what it looks like. And I will mention, in a certain sense, the quantum circuit diagram notation is hurting us here. This concept of teleporting gates is complicated to express in quantum circuits because you have all of these like Hadamards and C-naughts and measurements, and it just puts a lot of noise on the screen. There are other languages for expressing quantum computations, such as the ZX calculus, where these notions are much more implicit and natural. And so these constructions that I'm describing look much scarier in the quantum circuit notation. If this was a ZX graph, or if this was a topological space-time diagram of surface group computation, a lot of the details being shown here are gone and everything looks less scary. Anyways, again here, I'm just trying to demonstrate or show the concept of there's some input frame which the control system is going to figure out. And then that's going to allow later frames to be determined, which affect whether or not this Hadamard gate is present, which affect whether or not this measurement is flipped. And once all of that is dealt with, you can figure out the next part of it. You can figure out whether or not the next Hadamard happens and the next measurement is flipped, and so on. And this time from the end of one measurement to the next is the reaction round trip time. It's how long does it take me to do a Hadamard plus a measurement plus figure out what to do for the next Hadamard and figure it and tell the computer to do it. And like I mentioned, this is going to be the characteristic time that describes how fast our computation can run. So hopefully I've described all the pieces well enough that you can see how this might be turned into a way of running a quantum computation at a speed that's limited by your control system instead of limited by the code distance of your computer. It's still the case that the speed of your quantum computer matters, like your ability to apply a Hadamard gate quickly or slowly is important because that duration is in the round trip time. But there's no term here that depends on the code distance. It's the case that if you're using an error correcting code and it requires you to repeat measurements more often in order to become confident that a gate was applied, that doesn't appear here. So if you need a large code distance, this is a way of avoiding that being an overhead in time. So, right, to summarize reaction limited computation, you just use gate teleportation essentially everywhere. And you deal with all the complications of that by handing them off to the control system and having computer code deal with how exactly the Pauli frame moves through this whole thing. And you even rely on these automatic magic states to hide even more of the problem. And then your speed of execution is dependent on how fast can the control system go through these chains of dependent control Hadamards effectively. So hopefully that's clear enough. And now I'm going to go into an example of how you would use this in order to make something faster. So here is an adder where you have two inputs coming in. So in this case, the input, we can imagine for the moment, these are classical inputs. So these would be the bits of a 2's complement integer. So for example, A0 is the 1's digit of a binary number, and A1 is the 2's digit, and A2 is the 4's digit, and A3 is the 8's digit, and so forth. And together, these allow you to represent an integer. Because we're going to be running this on a quantum computer, you could have superpositions of different integers coming into the adder, but it would be completely fine to think about this adder classically, like as is the case with a lot of arithmetic circuits that appear in quantum computers. They tend to be actually described only using Toffolies and C-naughts, and there's not that many Hadamards typically, for example. So they actually often are reversible classical circuits. Regardless, here's an adder by QROM from 2004, where you have this sweep across the qubits of this majority gate, and then the sweep back of this other gate called the unmajority gate. And if you're actually running this on a computer, one of the things that might annoy you is that it takes a while to finish. So before this majority gate can start, this one has to have finished. And in order for it to finish, you have to do some controlled NOT operations, and you have to do this controlled NOT operation. And we would like to make this faster. And we're going to, of course, use the tool that I've been explaining for the rest of the talk, which is gate teleportation with these automatic magic states. So currently, the way this circuit is described, it has this carry propagation property where you have a carry input going into the circuit. And that this is analogous to if you do an addition on paper, as you go digit by digit, each digit produces a carry output or not, and then that goes into the next part of the addition. Here, that process is moving in a time-like fashion. So carry input comes in the past, comes out in the future. And we would like to instead have this, not actually true to what happens in the sense that there will still be a time ordering in the control system, but in terms of what happens on the quantum computer, on the main line of the quantum computation, we'd like to pretend that we can move our carries through space. And here I have kind of a cartoon of what that might look like as a circuit, which you can imagine is going to get a lot more complicated when we get into the details right here on this slide. So what this cartoon turns into is, of course, we're going to have this Bell basis measurement to bounce the carry back in time, and then this Bell basis initialization to bounce it back going forwards. And then we're going to have this if you recall, the circuit looks like a pair of controlled knots together and then a topology. So here is that controlled knot being applied. And then here's the topology being applied, and it's being applied using one of these automatic magic states, which is going to deal with all of the complications of making this work in terms of the gate teleportation, the fact that we're going to need frame corrections. And once we've done that interaction, we can go on and teleport back in time and start moving forward again with the carry out ready to be fed into the next part of the circuit. So we can chain these things vertically through space instead of horizontally through time. Once we have that building block, instead of making this slow wave, we instead make this very fast looking space-like movement. Now, it's important to always remember, although we're drawing it as if it's purely space-like, we do have a lot of automatic magic states going into the system, and we have a lot of routing qubits going out. See, these are the qubits where we have to apply control Hadamard's or not, and then measure them. So again, this is still serial in time. It still has a time ordering, but the time ordering is in the control system instead of in the quantum computer. Or actually, at this point, there are parts of it that are in the quantum computer, but again, the main important thing is that now we can run at the speed of the control system. Oh, I think I have a question. To what extent would this method could be a replacement of measurement-based quantum computation for low-depth circuit architectures like photon-based qubits? I don't think of this as a replacement to measurement-based quantum computing. Like, I actually think of this as being part of the spectrum of measurement-based quantum computation. So I don't think of it as a replacement. Right, so why do I keep talking about running at the speed of the control system instead of the speed of the quantum computer? Maybe this diagram will give some sense of why I would be talking that way. There's this notion out in the world that quantum computers are faster versions of classical computers, and this is completely wrong. It's actually the case that quantum computers are billions of times less efficient in a per operation sense than classical computers are. So this is a figure from a recent paper that the Google Quantum team put out, where we're kind of explicitly making this point in terms of, if you want to compute a NAND gate of 2 inputs classically, you can do that in a billionth of a transistor second. It would take, the resources consumed by performing that gate are 1 transistor for 1 billionth of a second on average. If you want to do the same operation under superposition, the amount of time goes up by 10 orders of magnitude, and instead of transistor seconds, you have qubit seconds. And qubits tend to be more complicated than transistors currently. So really, this is even underestimating the magnitude of the difference in cost. The only reason that quantum computers, that anyone even thinks about ever using them, is because they have more operations available. And there are particular algorithms where the number of operations you need is more than 10 orders of magnitude less. But you can maybe see how this leads to this idea of, oh my gosh, I have to get as much work off of the quantum computer and into the classical computer as I can, where things can go fast and not take up a ton of space. So we do estimates on the Google team of how fast do we think our qubits are going to be, how fast do we think our control system is going to be, how big do we think these factories are going to be. So here are kind of the numbers that we currently use. I will give the caveat that these numbers are always getting a little bit better. And there's a certain sense in which, you know, if this keeps happening for 3 orders of magnitude, then everything kind of changes in terms of what's expensive and what's not. But this talk is happening at a particular point in time where we believe the cost will be a particular thing, and so that's what I'll be talking in terms of. So when we do estimates, we sort of think of the factory as covering 100,000 physical qubits. There's a bunch of stuff that goes into this in terms of code distances and physical error rates and code thresholds. For the purposes of this talk, all that really matters is 100,000 physical qubits. And one of these factories will be able to output one of these magic states that we can use to perform a Toffoli gate every 150 microseconds. So here you can see that the sort of characteristic rate of the factory is 15 times longer than the reaction round trip of the control system that we would like to achieve. And so if you have a ripple carry addition like the Kekaro adder, you need 15 of these factories before you're saturating the control system and you're running that addition at maximum speed. So you need a huge number of physical qubits before you top out this reaction limited way of thinking about performing quantum computation. And this ends up affecting the cost of everything. So an example of something that this affects is classically, nobody uses ripple carry adders classically. Even all the way back to like the original microprocessors, like the Intel 8008, they're like 8-bit processor. That 8-bit processor had a carry look-ahead adder instead of a ripple carry adder, even though there's a depth of 8 when you have an 8-bit adder. But when we think in the quantum context, using a carry look-ahead adder instead of a ripple carry adder in order to reduce the depth has an overhead in terms of the number of magic states we need. So the best overhead that's published on arXiv is a 5x overhead. So it takes 5 times more Toffoli gates to implement a carry look-ahead adder than a ripple carry adder. And what this means is you need 5 times as many factories to run at the same speed as the ripple carry adder. So instead of needing 15 factories, we need 75 factories. And instead of needing 1.5 million qubits, we need 7.5 million qubits before the carry look-ahead adder is even keeping pace with the ripple carry adder. So you can see, unless you have a really, really large quantum computer, it makes no sense to use a low-depth adder. And this is completely opposite to the case classically, where even the smallest computers were using low-depth adders. And so all of these concepts of reaction-limited computation and the overhead of quantum computation come together and completely change a fundamental design decision that goes into like the most basic building block of arithmetic. So hopefully that maybe communicates why these things matter and how they affect the layout of everything. So I am actually pretty familiar with how these adders interact with the larger layouts, because I did work on a paper where we reduced the cost of factoring by a factor of 100 on a quantum computer. So what I'm showing here is a diagram from that paper, which is supposed to be kind of showing the activity at one particular point in time, or a few points in time really, during an addition. So there are a lot of pieces on this diagram are pieces we've already talked about. So for example, these red boxes are the magic state factories, which are producing the magic states that we want to use. And these pink boxes are what are converting them into automatic states. And these blue boxes are the majority boxes from the Kekaro adder. And you probably won't be able to see this through the compression on the video, but there's a very thin line going along here, and that's actually the carry qubit propagating through space. And once it gets to this side, it's basically going to stay here for a second, go up, and then the whole thing's going to repeat going backwards. So the carry is going to zigzag through space. The idea being that we're trying to create work and like consume automatic states and produce random qubits at roughly the same rate as the control system can handle it. So we don't do the entire 1,000-bit addition all in one go. We do it like 8 bits at a time. And actually, there is a little bit of concurrency in this particular implementation of the algorithm, where the left side and the right side are running separate additions simultaneously. Yeah, that's essentially everything that I wanted to cover, and it looks like I managed to hit the time almost perfectly. So to review, what I covered was, first of all, what is gate teleportation and how do you go about implementing it, like in full detail with the circuit? And then how do you use that and use the fact that the corrections for Clifford gates are very simple to pretend that there actually aren't any corrections, like they're all dealt with by the classical control system, and you don't think about them when you're running your quantum circuit, which lets you lay things out through space and time kind of very freely. And then the next 2 sections were sort of about dealing with the fact that not all gates have this property. There are non-Clifford gates, which have corrections, which aren't Pauli operations. And how do we make those act pretty similarly to this idea of we can just lay things arbitrarily through space and not think too much about how that all has to be resolved in the end. And then I went over an example of how you do this on addition, and then I talked about how this impacts fundamental design decisions that go into which circuits we pick to perform operations. If you're interested in learning more about these things, I have some papers that you can follow up on. So this first one is basically going over the same content, but in the language of the surface code instead of in the language directly of circuit diagrams. This next one is a different example of a paper by Daniel Latinsky that has a sort of different way of thinking about how you would embed a computation into a large-scale surface code. And in particular, this paper is thinking more in terms of the regime where you have one factory instead of many factories. And it's the first paper I'm aware of that introduced the concept of having a Clifford frame instead of a Pauli frame, which is kind of a neat idea. And then this bottom paper is taking these ideas and actually applying them to an algorithm in order to get a speed up. And that's all. Thank you for listening. I don't know what the end of talk convention is now compared to just waiting for people to clap. I guess we just go straight into questions.
Yeah, thank you, Craig, for the. Actually, this is becoming very dark in my office, so I am a little bit dark on the photo. So thank you a lot for this talk, for this nice talk about distillation and circuit. And I didn't say that at the beginning, but the people are getting used to it. We can ask questions via the Q&A, and I will try to translate it and to make it lively by communicating it to Craig. So, but I will start the discussion now with you, Craig. This is the concept that you expose didn't talk about at all about the way that basically you correct error, right? And as I understand it, you are like very much interested in surface code. Mm-hmm. So to speak. And this surface code, and my question is basically that this type of concept that you expose can be also like taken in other type of codes, like for example Bacon short codes or other type of codes that are more popular for other systems. Mm-hmm. with different characteristics. So I wanted to have your opinion about how this is efficient for other type of error correction codes than surface code.
Right. So it's actually sort of difficult to point at one thing and say this is the part that's specific to the surface code, because error correcting codes are very varied. They're all over the place in terms of what's limiting and what's not limiting. So for example, some codes, non-Clifford gates, are completely native, and you would never use magic state distillation. You would just directly apply the operations. One important property is how fast are your physical qubits. So, for example, if you're using an ion trap instead of a superconducting type of qubit, they tend to be a little slower with the ion traps. And this affects the trade-offs between how fast the control system is and how fast the quantum computer is. And somewhat surprisingly, I hope that's not coming through in the background. Anyways, somewhat surprisingly, making the physical qubits slower actually affects the trade-offs in a way that make it more important to use ripple carry adders. So if you're using the surface code on an ion trap computer with slower qubits, my inclination would be, oh, it's really important that we use a low def adder now because it's going to be slower and we have to compensate for it. But actually, when you actually go through the numbers, it ends up being even more beneficial to use the ripple carry adder in that case, mostly because the ratio between the sizes of factories, like the period of the factories and the period of the control system, becomes more disparate.
Okay. Still, I can continue because
Tristan, we have two hands up in the audience. So Nicolas and Natalie, if you want to ask something, please unmute and talk.
Sure, I guess I'll go ahead. I hope that's okay. I mean, my question is about the clock speed. I mean, I think that you're at Google, so we work in a cryogenic regime. My question is, how important is the proximity of control? I mean, the closer you are to the system, the less problems you have with impedance and wires and impedance of wires of the actual control to control the pulses. So when we talk about clock speed, do you think that the control has to be at the same stage of the cryogenic fridge?
Right. So I'll mention first of all that I'm not a hardware engineer, so I won't be able to talk about, for example, impedances. But I have talked with people, or people have talked to me about the trade-offs of putting the control in the fridge, like cold with the chip, or outside of the fridge. I think this is another thing that actually might depend on your error correcting code. In the case of the surface code, you have control that is in the fridge, from what I understand, tends to be, you want it to be very simple and very local. So you, for example, wouldn't have operations that were combining information from all the way on one side of the chip, 10,000 qubits away from stuff on the other side of the chip. And the thing that happens, particularly when you're doing this reaction limited computation, is you'll notice that these arrows are going all over the place. These arrows, in reality, are going to stretch across the chip. You have to combine information from the whole thing. And from what I understand, this probably requires you to get the information out of the fridge anyway. And so you might as well have your control system outside of the fridge, where you can use a computer that's spewing heat all over the place, and you don't have to worry about that so much because it's not inside a dilution refrigerator. Obviously, that will have an impact on how bad the latency is. Like, you have to wait for the signals to propagate out of the fridge to be decoded and so forth. But the thing we're the most worried about in this latency is not signals moving around and warming up and cooling down and so forth. It's all in processing the errors that are produced while the surface code runs and figuring out a syndrome for them. They're all in the syndrome extraction process. They're all in the minimum weight and perfect matching algorithm. Does that answer your question?
Yeah, somewhat. Thank you.
Thank you for your question. I can read off the questions here, or if there's, I think you mentioned there was another live question.
Yes, I think there is another. This is Nicolas, right, Thierry?
Yes, Nicolas, if needed, you can unmute and talk. Otherwise, we have two questions on the Q&R panel.
Let's move on to the questions on the.
Good thing.
Okay, so you can take it. Yeah.
Yeah, the first question is from Daniel Esteve. You talked about the quantum adder. What about a quantum multiplier? How complicated would it be? So basically a quantum multiplier, the way that we tend to implement them is just a series of quantum adders where, for example, if you want to add a register A multiplied by register B into a register C, the simplest way that you could imagine doing that is you would say, if the ones bit of register A is set, I would like to add register B into register C. If the twos bit is set, I'd like to add register B into register C, shift it over by 1 so it's multiplied by 2. And then if the fours bit is set, do the same thing, but shift it over by 2 and then by 3 and so forth. So it's a series of control adders. There are techniques, in particular, if the value you're multiplying by is classically known, which is the case in Shor's algorithm, you can apply some optimizations to make that a little bit more efficient, but ultimately it does come down to it's just a series of adders. There are, of course, very fancy multipliers like Karatsuba multipliers or multipliers based on the fast Fourier transform, but the overheads of using them compared to the simple thing tends to make them not worth it. It's very similar to the case where we prefer ripple carry adders compared to carry look-head adders because the overhead is lower. And it ends up being the case that the simple thing is the most efficient. Okay, next question. I see. That question was actually from Emmanuel Fleurin, not from Daniel Lacey. Next question is from Rob Whitney. Do your estimates for factory sizes include error correction within the code itself, i.e. correcting error in Z gates, C naughts, etc., acting on the data qubits? Yes, those factory estimates include everything. They assume that the qubits that the factory is made up of are logical qubits, and those logical qubits are correcting errors that occur on the physical qubits. And they account for the fact that you inject your physical states in a sort of noisy way, and because they're so noisy, you can use a small code distance initially, and as you distill the state more and more, the code distance has to increase over time. Also, we keep in mind the fact that these factories have some finite error rate, and like we tend to come up with fixed factory designs that will, for example, be good for 10 billion Toffoli gates. And then if we want a larger amount of Toffoli gates than that, then we'll switch to some other factory design because you tend to have to repack these things all the time. So hopefully that answers that question. Rob says, okay, great, thanks.
Okay, maybe I have like a question for you, say, concerning the asymmetric noise that you can have in quantum circuits. So how does that affect the estimation that you make on the overheads? If you have, like, for example, a faster dephasing time than flip time, do you think that it will matter, or do you see ways that you can use that?
Right, so I'm aware of this research that looks into what if your noise model is extremely biased towards one type of error. So for example, what if the amount of Z errors that you incur is 1,000 times greater than the amount of X or Y error? And you can actually take advantage of this in the surface code, and you can adjust things so that it is more resilient to Z error. The main issue is this puts a lot of constraints on your hardware. So for example, you can never apply a Hadamard gate ever in hardware if you want to maintain this property, because the Hadamard gate will change Z error into X error. So your hardware has to natively support applying applying 2-qubit interactions without changing the basis of the qubits. And additionally, the way you apply those 2-qubit interactions also has to have this noise preserving property. So even though you're applying a controlled knot operation, which would tend to introduce Z-type noise on the control and X-type noise on the target, just from the fact that those are the two bases you're interacting, you need to somehow avoid that. So I think like the theory side of using biased noise is in a pretty interesting place. Like I think the case has been made that if you can do it, that it's extremely interesting. I'll again say I'm not a hardware engineer, but from my perspective as not a hardware engineer, I'm kind of skeptical that you can make physical systems that actually really preserve this property as you execute the full surface code study. If you can, that's great, but I don't know. To me, it seems almost contradictory to say I'm going to apply a controlled knot operation, but I'm not going to have controlled knot-like noise.
Okay. Okay, I think that we must wrap up now. So thanks, Greg, for the next talk and the nice discussion at the end. And
Thank
we
you.
will